right. Okay. Guess you're set for today.
Yes.
Let's pray. Father, we thank you for today. Thank you for your message. Thank you for your love. I pray as we start now, Holy Spirit, grant us wisdom, understanding in the name of Jesus. Blessed be your holy name, Lord. In Jesus' name I pray.
Amen.
They'll be looking at chemistry and also it will be awesome for us. The last time we started off with periodic table. Okay, and in the periodic table, one of my major goals was that at the end of this training, that's a training, seriously. Okay, at the end of this class, we should be able to know how to construct. We should be able to know how to construct our own periodic table. Did I ever give you did I ever give you? Okay, that you should construct. Okay, I don't think I've given you that. Now, we looked at periodic table, the periodic law, and okay, having looked at those things, this time now we'll be looking at how to principles and rules of filling in electrons. The principles and rules of filling in electron. Actually, we did establish the fact that we have orbitals such as sp(d)f orbitals. Okay, now what we've seen, how do we fill in these electrons? How do we fill them in? You don't just fill electrons like that. They have a way of filling in electron, and that brings us to one of the principles called the Aufbau principle. The Aufbau principle. The Aufbau principle. That is AUF, BAU, Aufbau principle. Right? Okay. Now, the Aufbau principle. What's the Aufbau principle? The Aufbau principle states that electrons are filled in orbital. Electrons are filled in their orbital in order of increasing energy levels. The Aufbau principle states that electrons are filled in their orbital in order of their increasing energy levels. That's actually what it says. Electrons are filled in order of their increasing energy levels. All right. This means that 1s is lesser than 2s, lesser than 2p, lesser than 3s, lesser than 3p. Don't worry, I'm going to explain that now. Let's see the Aufbau principle come into play here. An example is this. We have 1s, we have 2s, we have 2p, we have 3s, we have 3p, 3d, we have 4s, 4p, we have 4d, and then we have 4f, okay, and let's stop at 5s, 5p, 5t, 5f, 5g. Let's assume we will rarely have something like this. Okay, now the Aufbau principle, how do we draw the Aufbau principle? How do we go about it? This states that they are filled from 1s, then we come to 2s, from 2s, sorry, I think I should use a more, okay, this is cool. Let me change it to another color so it's okay. Okay, we have this, from 2p 3s, from 3p we have 3p 4s. All right, from 3p 4s we have 3d 4p 5s. Okay, we have oh, okay, um okay, we have this. Okay, we have this, we have this, we have this. Now, what does this mean? Let's see the relevance of this. This means that if we are filling any electron for electronic configuration, we have 1s, we have 2s, we have 2p. From 2p, we have 3s. From 3s, we have 3p. From 3p, we have 4s. You see, we don't have 3d. First, we don't have 3D coming up. Rather, we have 4s. 4s, we have 4p. Sorry, 4s, no, not 4p. That's wrong. From 4s, we have 3d. From 3d now, we have 4p. Now from 4p, we have 5s. From 5s now, we have 4d. From 4d now, we have 5p. All right, do you see the way it is going? Do you understand that?
Yes, sir.
Okay, so this is the half-bar principle. Now, we're going to see the application of this half-bar principle. We're going to see the application of this now. Now, zinc is actually the 30th element. I need you now, as an example, to give me the electronic configuration of these electrons for zinc. Zinc is the 30th element. I want you to write this now for zinc. Give me the electronic configuration of filling of these electrons for zinc. I guess it's something you can do, right?
Yes, sir.
All right. So I'll need you to try that out now.
One S2, two S2,
Have you written, have
two
you done that
P.
immediately?
Yes.
Really? Oh, good. I'm coming. Could you write it?
Yes, sir. Should I also draw it or should I only write it?
No, no, no. Just write the one S to just. Okay. I just write it. Or do you want? Okay, I'm coming. Let me see if I could shift this. I want to keep this. Okay. Okay. Okay, just use somewhere here to write it. This area here. Good, good. I like what you're doing now. Right, you can continue. You're done, right?
Yes, sir.
Okay, we have a 10, 12, 18, 20. Good. I like this. I like that fact you put. So this shows that zinc is in the D block. The D block of the periodic table. The D block is actually the area of the area of transition elements. Okay. it belongs to period 3. Okay, this is a good one. Awesome. Okay, now this is just an example. This is just what we're trying to say, that 3p comes, and 3p, then we have 3d. After 3p we have 4s, 4s to 3d. Yeah, most times students tend to confuse this part because of this. They bring 3d first because of the number, but thank God you've been able to establish the fact that 4x comes before 3D because 3D is higher in energy level. Okay, we've talked about the Alva principle. The next one we want to talk about now is the Pauli exclusion principle. The Pauli, or the Pauli exclusion principle. Pauli, 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 Pauli's Li apostrophe S exclusion principle. Now, the Pauli exclusion principle states that in two electrons in the same orbital of an atom. The Pauli exclusion principle states that two electrons. Pauli exclusion principle states that two electrons in the same orbital of an atom. Two electrons in the same orbital of an atom cannot have the same values, for all quantum numbers, cannot have the same values for all quantum numbers. Okay, I'm going to explain that. What this means is that usually first electron in an orbital is assumed to be entered with an up spin, and the second electron is done to do with a downward spin. I'm going to explain this now. The Pauli exclusion principle. This is exactly what it means. For example, let's look at this. Nitrogen. Nitrogen has an atomic number of what? Nitrogen has an atomic number of what?
7.
7. Good. Okay. Now we are going to write it. We have 1s2, 2s2, and probably 2p3. Okay. If you are to draw the filling of electron, okay, what this means is this will be drawing something like this. This is for 1s2, 2s2. Now for p, I'm going to have a line like this. Okay, remember the s can only contain 2 electrons. Okay, the p can contain 6 electrons but has a subshell of 3. Okay, now this is exactly what we mean for the Pauli exclusion principle. That the Pauli exclusion principle, this is exactly what it means, that okay, we have it feels, oh sorry, we're going to have pointing downward. We're going to have something like this, and this one goes upward. Okay, coming. I think I'm not, this thing is actually giving me. Okay, I'm going to have a coming. Oh no. Okay, let me use a different color then. Okay, 1s, 2s. Let me use that for them. And then I would use this one. Then this one goes up. This one goes up. That means they're trying to say that they cannot have the same. We can have something that will have a one, one. No way. It has to be one goes up, the other one points downward. Now for P3, this is for the S block. This is for the 1s block. This is for the 2s block. Remember, it has just one shell and can contain just a maximum of 2 electrons. Now, but for the P block has three orbital. Sorry, six can contain 6 electrons and has 3 suborbitals. Okay, we do this one. We do this one. So for the 2p3, for the 2p, the P block, you can have one electron being filled, one electron be filled, one electron be filled. So what polar exclusion principle was trying to tell us that for all quantum numbers, no shell, no orbital can have the same number of electrons. When you are filling them, you can't have them having they cannot be filled like this. Rather, they have to be filled one going up, one coming down. That is one of the rules of polar exclusion principle. Okay, do you understand that part?
Better.
Now, okay, the next one we'll be talking about is the Horn's rule of maximum multiplicity. Horn's rule of maximum multiplicity. Horn's is actually spelled Hunds. Horn's rule, Hund, then apostrophe S. Horn's rule of maximum multiplicity. Now, what has this rule got to tell us? This rule states that electrons occupy each orbital singly. Electron occupies each orbital singly first before pairing takes place. First, before pairing takes place in a degenerate orbital. Electron occupies each orbital singly first before pairing takes place in a degenerate orbital. All right, do you understand what that means? Don't worry, I'm going to explain that, but do you understand?
Yes.
Sorry?
Yes, sir.
Okay, tell me what you understand by that.
It means that before you move to another shell to go and pair it, you have to complete the first shell.
You have to do what? Sorry, I didn't get that, please.
Complete the first orbital.
Okay, correct. Now, exactly what you just said.
Orbital to pair. You have to complete the first one.
Okay, correct. That's awesome. Let's see. Okay, exactly what it means that you see, oxygen has an atomic number of what?
Eight.
Okay, 8. That means we should be having 1s2, 2s2, and then we should be having 2p what? 2p4, right?
Yes.
Okay, so that means for 1s2, we fill the one, we fill for this. For 2s2, that one we can fill Hunt's rule, we apply more when we come to the P block. Okay, Now, but for this 2p4, we only have 3 suborbital. Now we have to fill each first. One, we fill this one, we fill this one. We won't say, it is very wrong for us to say we fill 1 and 2. No, you fill them first. You fill this one first. Okay. When they are all filled up, you come back to say, okay, this is remaining one more, 4. That's the Hund's rule. You come back again to fill this. The same thing also happens in fluorine. Fluorine is atomic number what?
9.
Okay. At having an atomic number of 9, we do Hund's rule also applies there. Now for Hund's rule, we do the same thing. Okay. Okay, for Hund's rule, we come back. Okay, it's going to have, let's do this. 1s2, 2s2, and then we have 2p what? 5. Okay, we have we fill this, we fill this, we come here, we fill this. Now the same thing, we'll come here, we fill them first. Then we come here, we fill this, come here, we fill this. Now, most textbook, you're going to see something like this. I don't know if you've seen that, px, py. Have you seen that before? pz.
No.
Now, this one, you're going to have two, most of them will be carrying 2px. This is just to show for the p block. Then pz. Okay, so this is exactly what Hund's rule was trying to tell us, that before filling the orbital, before filling them, they must be filled. You must have filled them singly first before you go to their degenerate orbital, and that's exactly what Hund's rule was trying to tell us. Okay, I believe you understand that part, right? Are you there? Hello? Hello? Okay, you're back, right? Hello? You're muted, please.
Yes, sir.
Okay. Now, we need to understand groups and period now. We need to understand groups and period. Remember when I said one of our goals is to be able to construct the periodic table. Okay. Now, when we talk about groups, groups are, when we talk about groups are vertical. You see the vertical, periodic table is divided into vertical and horizontal. Now, the vertical parts, the vertical rows are called the group. The vertical are called the group. Now, the horizontal are called the period. Now,
Period.
one of our goals, I said, is to be able to construct the periodic table. We should know, now that we've known that, now that we've known this, that the vertical are the group, the horizontal are the periods. So let's delve into um, creating, let's dive into creating our own periodic table. We should know the periodic table. We're going to start with the periodic table of the first 20 elements. Okay, we know definitely, um, we know definitely that they're divided into, okay, sorry. We can definitely construct a periodic table. I think this could help us. Let's do this for group. Let's do this for group 1 and 2. This would definitely help us if we know. For example, I'm just going to do a very few number, then I'll leave you to complete the rest. Okay. Now, let's see how do we create the maybe 5. Let's say 5 of them. 5 hydrogen. Hydrogen, because of its atomic number 1, has just 1 proton and no electron. So if these are, we call these groups, and these are periods. Okay. Okay, I'm coming. I think we could do something creative here also. I could okay. I'm gonna call this my group. Now these are the horizontal, the group. The vertical is the group actually, and this is the period. So hydrogen, I can place hydrogen in group 1. It can be in group 1. It can also, hydrogen has a unique property of being in group 1 and being in group 7. Hydrogen has a unique property of being in group 1. So let's put hydrogen in group 1. Okay. Hydrogen, helium. Let's come to helium. Helium has just 2. Every atom, I said previously that every atom tries to obtain 2 states. Number 1, the duplet and the octet state. Any atom that has a duplet state already, that means all its electrons are duplets. That atom is already filled up already. So helium has just 2. That shows that helium is filled up already. So helium will belong to the group of what we call the noble gases. Noble gas, helium is filled up already. Helium is can only has attained the duplet state, and like I said, all atoms try to obtain duplet or octet state. So helium cannot be in group 2. Rather, helium would be in group 8 or group 0. They are called the group of the inert gases, the rare gases, or we call them noble gases. We call them inert gases, rare gases, or noble gases. So if that's the case, we're going to call, that means we will need to construct, okay, this is actually group 1. What we just did now, this is group, let's put this as group 1. Group 2, okay, we would have to create another one. We are going to, in periodic table, there's a middle like this. These ones are for the transition element from that they're in between group 2 and group 3. So we leave that line there. Okay. Then we create this other aspect where group 3 to 8 will stay. Group 3 to group 8 will stay. Okay. Now these are the group of transition elements. Now let's come to, this is group 3. Group 4. Group 5. Group 6. Group 7. And we can keep that one as group 8. So I'm going to take okay. Now let's change this. Let's make this group 3, group 4, group 5, group 6, group 7. We are calling it group 8, or we can call it group 0. All right. Okay. So we've just established the fact that helium, remember, helium belongs to group what? Group 8, isn't
Yes.
it?
Yes.
Okay. Now, what's the next element? Hydrogen, helium. What's the next one?
Lithium.
Lithium. Okay. Lithium has an atomic number of 3, isn't it?
3.
And that means we're going to be
Yes.
having 2,1, right?
Yes.
Okay. 1 means that it belongs to group 1, right? This one,
Yes.
this one belongs that it belongs to group 1. So we put lithium here. Lithium belongs to group 1. Remember, what will be the period of group of lithium? Lithium will have a period of what? Period of 2, right?
Yes.
Okay, so you see now, this is the period. We have period 1, we have period 2, we have period 3. So lithium has a period 2, group 1. Awesome, awesome. Yeah, our table is becoming filled up. Okay, now let's continue. The next one after lithium is what?
Beryllium.
Beryllium. Beryllium. Okay, now let's look at beryllium. Let's look at beryllium. Beryllium have atomic number of what? 4. Now that becomes 2,2, right?
Yes.
Okay, beryllium becomes the first in group 2. Group beryllium now becomes beryllium will not be here because it will have a period of period 2, isn't it? The period of beryllium will be period
Yes.
2, isn't it?
Yes, sir.
Okay, because beryllium will be in a period of period 2, we cannot put beryllium here. So I'm going to remove the beryllium here and bring the beryllium down. Do you understand that?
Yes.
Okay. Now, the next one after beryllium is what? Is boron. Boron has an atomic number of 5. All right.
5.
Okay.
Yes.
We have that becomes 5, 2,3. Okay. Boron so from there, that means boron becomes the first to be filled in group 5, in group 3, and has a period of 2. So this becomes boron. Okay. Now on this table, I need you to fill the others for me. On this table, I need you to fill the others. Now we've done everything. We've done okay. Now I need you to fill. Okay, just let's fill till. I guess you should be able to fill till. You'll be able to fill to 15 if possible. Wow, you're doing well. Wow, you have to complete this to 20. I'm enjoying this. Awesome. This is beautiful. All right. Good. I'm so proud of you in this. This is awesome. This is beautiful. Now, I'm going to leave you to do. I'm going to leave you to do this. This one in what do you call it? I'm going to leave you to do this for transition methods later on. That will be your assignment. Don't worry. Not here. All right. Now I need you to notice something. I need you to, let's get to know the block now. Are you there?
Yes, sir.
Okay. Let's get to understand the block of elements now. Now we'll be talking about the S, the P, the D block. Okay. Hydrogen has just one proton, so it's going to be 1s. So this is the S. Okay, let's look at lithium. Is lithium having let's know which element belongs to S, P, and D block, because it's very, very important for us to know the S, the P, and the D block. We need to understand those things. Okay. I want you to take note of lithium. Please, let's try this out. Lithium, sodium. Lithium and sodium. Where do you think, let's do lithium. Lithium belongs to, that's 3. That becomes 1s2, 2s1, right?
Yes.
Okay, let's do potassium. Potassium is K. Potassium is 19. So we're going to be having 1s2, 2s2. As I'm doing potassium, I need you to do calcium for me. I need you to do calcium as I'm doing potassium.
Okay. 1, 2s2, 2p6, 3s2, and 4s2.
Okay, so calcium is in, what is the, can you tell me the last thing in calcium? The last
4s2.
4s. Look at potassium. Potassium is 3. Oh, potassium is 4s, sorry. Potassium is 4s1, while calcium is 4s2, right?
Yes.
Okay, now what does this tell us? This tells us a whole lot. That means group 1 and 2 elements. Group 1 and 2 elements belong to what we call the S block. Group 1 and 2 elements. How am I going to do that now? Okay, let me find glue. Group 1 and 2 elements. Oh no, I wish I can do this. Group 1 and 2 elements. Let's see something. Group 1 and 2 elements. I'm going to do something. Group 1 and 2 elements belong to what I call, let me do them like this. Group 1 and 2 elements belong to what I call the S block. They belong to the S block, X block family. Group 1 and 2 elements, they belong to the S block, the S block, the S block family. Okay, we have established the S block for group 1 and 2. All right, let's come to boron. I need you to do this for me. You're going to do, it belongs to the S block family. Okay, I need you to do this. You're going to do for boron, you're going to do for carbon, you're going to do for nitrogen, oxygen, fluorine, and neon. Tell me what is the last thing you see there? For boron, for carbon, for nitrogen, for oxygen, fluorine, and neon. I need you to just give me the last thing there, just the way we did for group 1 and 2. What block do you think they'll belong to?
P.
Are you serious? Are you
P
saying
block.
P everything?
Yes.
Really? Did you just do that now?
I've already written the configuration.
Okay, written that before now? Or you wrote it today?
Yes.
Okay, before now. All
I've
right,
written it
all
before
right.
now.
You
Inside.
said?
I've written it before now.
Okay, all right. Beautiful. Now, this area from group 3 to group 8, that means group 3 to group 8 belong, group 3 to group 8 belong to the family of the P block. Group 3 to group 8 belong to the P block. All right? Okay. Now, if we have understood this fact for the first 20 elements, so imagine the first 20 elements just rotated between S and P block. Okay, where we'll be having a greater understanding will be at this side, at these beautiful places. These places are really called the transition metals. The transition metals, most times they are used as catalysts. Whenever you hear us calling catalyst, this is where we get them from. We get them from this block here. Between the block of between group 2 and group 3, they are called the transition elements. The transition elements. And tell me, these guys belong to what we call, the F block. Sorry, the D block. The D block. These guys, they belong to the D block. We've not done them yet. These guys, they belong. Okay. These guys belong to what we call the D block. Okay. Okay. Oh, so do you see now that it's very easy for you to have your periodic table yourself? Okay, sorry, what are you doing?
I said yes, sir.
What are you doing?
I'm drawing the periodic table.
Sorry?
I'm drawing the periodic table.
Okay, you're doing yours now.
Yes.
Oh, beautiful. Okay, let me know when you're done then. So now we've established the fact that you can perfectly do your own, construct your own periodic table. Now, this is one of the very important skills you need in chemistry. Very, very important that you should be able to get your own periodic table. You should be able to form that yourself. At least you should be able to do for the first 30 elements. First 30 elements is awesome. Wow. Beautiful. If you can do for first 30 elements, beautiful. That means you've really, really gone a long way. You can. And I know it's something you can do. Now, from the position of these various elements on the periodic table, we've gotten to understand that electron arrangements seem to stand out. Elements with 1 and 2 electron in their outermost shell, they belong to, that's the group 1 and 2 elements. They are called the S block elements. Now, the P block elements have in their last electron, they have the P orbital, and then they're also called the P block elements. But elements that have their last electron in the D orbital, we call them the D block elements. While those that have F block element as their last electron are called the F orbital. Now, there are some things I really don't want to move that periodic table because I'll be using that to explain a whole lot of things. Now, moving across a particular period of the element, two elements are present in the S block and stuff like that. We are going to be seeing that there is a diagonal division. Now, we'll notice that one thing you've noticed that S block elements are metals. Have you noticed that S block elements are metals? From our periodic table, have you noticed that S block elements, all of them are metals? Look at them very well. Sodium, lithium, beryllium, magnesium, calcium, potassium. Have you noticed that all of them are metals?
Yes.
Okay, now look at the P block elements. P block, all of them are non-metals. Jesus Christ. Boron, calcium, nitrogen, oxygen, fluorine, all of them basically non-metals. Okay, now you see, we've gotten to understand that, okay, now D block elements, I did mention to you that D block are all transition metals. They're transition metals in sense that, number one, we have properties of transition, those guys, D block. I told you that they can be used as catalyst. Okay, we're going to come that. I'm going to explain that later on. But F block elements are those kinds of elements we call them the actinide and latinide series. Lanthanide series and actinide series. Those are the F block elements. We call them that. We call them the lanthanide and actinide series. That means they are the heavy rare earth metals. We call them the rare earth metals and the heavy rare earth metals. Okay. Now, another thing we should note from this periodic table we just drawn is this, that there is a diagonal division of the elements into metals and non-metals. There's a diagonal division into elements, into metals and non-metals. Now, metals are found on the left side. Metals are found on the left side, and non-metals are found where? At the right-hand side. Okay, this is, now, this thing alone now, this is trying to tell us that from this place now, this S block, we have them as metals. Okay, these guys here now, we have them as non-metals. Why this other guy below, we have them as metalloid or semi-metals. Okay, yeah, so that's the periodic table. Now, we have gotten to establish those facts. Now, let's talk about the properties of this transition element. Let's look at their properties. Why are they different? You see, they have a special place in the periodic table. They are very, very different set of guys. Different set. Okay, I'm going to be using that to explain them. I have an acronym I gave for their, I think, what did I call that? I think it was PAVOC. Okay, let's see if I'm going to explain that. Okay, I called PA as paramagnetism. That's one of the characteristics. PA, I called it as paramagnetism. Paramagnetism. Okay, transition elements, they are paramagnetic because of the presence of unpaired electron in the d orbital. The presence of unpaired, they have some unpaired electron in their d orbital. Okay, now what is paramagnetism now? Paramagnetism is the ability of an element to align to the poles of a magnet. The ability of an element to align to the poles of a magnet. Remember, a magnet has the North Pole and the South Pole. So the ability of an element to align to the poles of a magnet, just like zinc, just like iron, Fe, iron, like zinc, iron, we have scandium, we have titanium, we have chromium, we have titanium, scandium, chromium, zinc, iron, all these things are paramagnetic elements. So they have the ability to align to the poles of a magnet, and that's why we call them. That's one of the properties of those transition elements there. They are paramagnetic. Have you gotten that down?
Okay.
Okay, number two, that V you see there is variable oxidation state. Variable oxidation state. Really, you remember when we're doing some things, we will see sometimes you look at this. Okay, look at this. Look at this. Have you seen iron? So you know Fe is iron, right?
Good.
Okay, look at these things I'm writing now. Now, what's the difference between this FeO and Fe2O3? Do you know their names?
Iron 2 oxide and
This is iron 2
iron
oxide.
oxide.
What is this one? FeO is what?
Iron 2 oxide.
And what is Fe2O3?
Iron oxide.
Sorry? Okay, let me tell you the difference now. Okay, now look at the difference. You can see iron exhibiting two oxidation states. The first one is iron 2. The second one is iron 3. This is Fe, this 3 is for iron, this 2 is for oxygen. Imagine just one element exhibiting two states. Can you imagine that? That's serious. All right. So one of the properties of this p block element is that they have variable oxidation states. Iron can exist as iron 2. Iron can also exist as iron 3. All right. Now, why is this possible? Why do they have variable oxidation states? Now, transition elements exhibit variable oxidation state because, please write this because it might be asked that, because they can lose electron. Because they can lose electron from both 4s and 3d orbital. From both 4s and 3d orbital for bond formation. They can lose electrons. They can lose electron. You know that variable oxidation state is where we start having transition elements or transition metals become the metal where we start having 4s coming before 3d. That's where we are going to have those sorts of things. Okay, so they can lose electron, number one, from both 4s. They can also lose electrons from both 3d orbital for bond formation. So that's why we can really have ion coming up as ion 2 and ion 3. Okay, all right. Now, look, let's come back to our acronym. Let's come back to our acronym. Okay, this VO was for variable oxidation state. The CO is for complex ion formation. Complex ion formation. Complex ion formation. Now, transition elements actually can form complex ion due to the presence of vacant or empty d orbital. Transition elements can form complex ions due to the presence of vacant or the empty d orbital in their ion. Empty d orbital in their ion. So because of that, they can form the complex ions. They can form complex ion. And the last C that we see there, is catalytic ability. I've told you this. Sorry about that. Catalytic ability. Now, The catalytic ability of transition elements is due to the fact that they exist in different oxidation states. Because they exist in different oxidation states, they can be used as catalysts. Because they exist in different oxidation states, they can be used as catalysts. And not only that, remember, number one, they exist in different oxidation states, which we have established that fact. Number two, the partially filled d orbital allows the exchange of electrons to and from molecules. The partially filled d orbital allows the exchange of electrons to and from molecules, which enables them to act as a catalyst. Remember, what is a catalyst? A catalyst is a substance that alters the rate of chemical reaction. When we talk about catalysts, we're talking about substances that can alter. Most times people say a catalyst speed up the rate of chemical reaction. No, a catalyst is not only responsible for speeding up the rate of chemical reaction, a catalyst can also speed down. That means it can be a positive catalyst. That means increasing the rate of chemical reaction. A catalyst also can also decrease the rate of chemical reaction. An example is this. I'm going to give you an example of this. What I mean, it's if I take a wood that is wet, a bit wet, or a damp wood, or yeah, moist wood, when you put fire to that wood, do you think the wood will burn?
Yes.
With the wet wood, would it burn well as it's wet?
No.
No, good. It's not going to burn more like that. But if I take that same wood that's wet, I make sure that I wet that wood with petrol, with fuel, everything that can burn, put it inside the wood. What do you think, when I put fire into that wood, what do you think will happen? Is it going to burn well?
Yes.
Definitely. So the fuel acts as a catalyst. The fuel there acts as a catalyst. It speeds up the rate of chemical reaction of the wood, increase the rate of combustion of the wood. So the fuel there is acting as a catalyst. Okay, so I just had to explain catalyst, what it's all about. All right. Let's come to families of elements. Families of elements. Families of elements. Now, in fact, one of the things I'm so happy well done, it's the fact that we have been able to arrange those elements into groups and periods. Now that we have arranged them into groups and periods, we're going to be bringing forth their names. They are actually family. They are beautiful, awesome family. These guys are really wonderful family. Okay, when we talk about family, that means in a family we have things that happen in a family. We have things that happen in a family. So if these guys, are referred to as if these guys are family, so that means in a family, what do you think will happen in a family? They are going to exhibit some similar characteristics. All right, you understand that, right?